Hello students, good evening. Welcome to another class by Vedantu Karnataka. So today we will be doing the second part of your past batch. Can you all let me know if I'm live, audible and visible properly? Yes. Students, good evening. Yeah, I can hear myself here. Hi everybody. So there was a small correction. Yesterday in my video I said the class would start at 4, but today I had to start at 3:30 because of some other personal reasons. So can you all go tell your friends that the class has started and it's at 3:30? Can you send the link to all your friends and tell them it has started half an hour early? Can you all do that, my dear students? Yes, Singer. Hi, Singer. Hi, Sahana. Hi, Ishwara. Ishwar. Hello. Yeah? Can you all quickly go tell your friends also because we started half an hour early. I told them it's at 4 today. Can you all please quickly go bring them? Hi Aditi. Hi Ganavi. Yes. Super. I think everybody's here. Alright. Hi Apu. Hi Lahvi. Hi Preetam. Okay. So let's start. So today we will be discussing the rest of the chapters. Yesterday we finished almost half. Today we will be discussing the rest. And some of you had requested for MCQ. So I've added few MCQs also at the end of the session. So once we discuss all the chapters till the end, we will do some MCQs as well. Okay? Is that clear? Yes? Are we all ready? Let's move on to the class. Yes. Good afternoon, never give up. Nice YouTube name, never give up. Yes, I hope you never give up in life. Okay, so let's start. So, in the last class, hi Rupa, hi Sakina, hi Savio. PDF is there, Apu. After every class, I upload the PDF in the description box. So, last class PDF is there in the description box. So, this class is PDF. After the class, I'll upload it in the description box. Duration is not less than 2 hours because we have very few chapters to finish and then we'll do some MCQs as well. Alright, let's start. So last class we discussed till mutual inductance of two long coaxial solenoids. So today we will start with alternating current. What is alternating current? Alternating current is current that can flow in both the positive and the negative direction. So all of you know there are two types of current, direct current and alternating current. Alternating current can flow in both directions. Okay. The first thing that you need to know in alternating current is about transformer. So what is a transformer? A transformer is it's a device that can step up or step down the voltage. Now, why do you need to do that? Okay, so every time, from our main power, let's say the main power grid, from there, current is generated. So this current has to travel a long distance before it reaches your house. So, see, current has a property that it heats up the wire in which it travels. So, if high current passes through these wires, the wires will start heating up and a lot of energy will be lost as heat. So, to prevent that, what you do, you use a transformer. And what you will do is you will decrease the value of current and increase the value of voltage, but maintaining the power. What is the formula for power? Power is VI. So the value of power is maintained, but current is reduced and voltage is increased. For example, imagine initially it was 2 into 5. Voltage was 2, current was 5. What you will do? You will make the voltage 5 and the current 2. Okay, so now this low current passes through long distances. So the advantage is it prevents heating. So when it goes to long distances and then it reaches your house. Before it reaches your house, there will be another transformer. You've seen transformers on roads, right? There will be another transformer that converts it back. So 5 into 2 is converted back into 2 into 5. Okay, so the low current is converted back to high current. So that is what a transformer does. It helps in transferring current through long distances by increasing or decreasing the value of voltage. Is that clear? Yes? Okay? Yeah. So now there are two kinds of transformers, step-up transformer and a step-down transformer. And the main principle of a transformer is mutual induction. So what happens? You can see this is the structure of a transformer. So initially there is one coil which is a primary coil and Along a soft iron core, the other arm is a secondary coil. Okay. So you have a primary coil and a secondary coil, and the main current goes to the primary coil. Okay. So current is given to the primary coil. Now, because of mutual induction, this current is passed over to the secondary coil. Alright. Now the secondary coil has the current and that is given to the output. Alright. Now, if your input is low and you want a high output, for example, if the input voltage is 2, but you want the output voltage is 5. So you have more coils on the secondary. That is because you need more output. If you want the other way around, you have more coils on the primary. Okay, is this clear? So the principle is mutual induction. The current given to the primary coil induces a current on the secondary coil. Last class I taught you what mutual induction is. The change in current on one coil would produce an EMF on the other coil. Is that clear? Alright. Okay. Next is the different forms of energy loss in transformers. So the first one, loss due to heating. Okay. So sometimes, in your transformer, there is a lot of heating between the coils. So that is one loss. Next is loss due to flux leakage. Okay. For your exam, you only need to know what these are. Loss due to eddy currents, loss due to hysteresis. I've just added a small a small sentence for you to read and understand. Alright. Loss due to flux leakage is what? All the magnetic flux in the primary is supposed to reach the secondary, but it does not. Some of it leaks in between. That is flux leakage. Now, eddy current is a current in the iron core. So we don't want the current in the iron core, and that can heat up. So what we want is from the primary to reach the secondary, but it does not. Sometimes it heats up. So that is called eddy current. The current lost in the iron core that produces heat. Next is hysteresis loss. You might have learned what hysteresis is because it is because of the magnetization and demagnetization. When does that happen? Whenever current passes through a coil, there is magnetic field. So that when the current is switched off, the magnetic field is gone. So this magnetization and demagnetization of the core will produce some loss. That is loss due to hysteresis. Okay? Is this much fine? Chapters only. Okay, some of you wants MCQs and problems, no? I am going to do some MCQs in today's class. At the end of the lesson, we will do some MCQs which could be helpful for you. But this is not a video for scoring out of out. This is a video for scoring well. That's all. Okay? Because you have to practice more for scoring out of. Alright? Yes. Mohit Kumar, RCB match is going on. Every time I take a class, RCB match is going on. Yes. Alright. Hello, the Desai. Okay. Next is the phase angle between voltage and current. Alright. So, first thing, for a pure resistive circuit. Okay, so you need to know what is the angle between voltage and current for different circuits, for 4 different kinds of circuits. First one is a pure resistive circuit. Okay, so the phase angle for a pure resistive circuit is always 0. That means voltage and current have the same phase. The graphs will be the same. Alright, now for an inductive circuit, there will always be a 90-degree lag. See, what do you mean by same phase? If this is voltage, current will also be having the same phase. That is, this will be current. Now, a 90-degree phase means it will start different. There will be a 90-degree phase. Now, if it's a pure capacitive circuit, it will have a minus 90-degree lag. Alright. So, in pure inductive, what happens? The current lags voltage by 90 degree. If it's a pure capacitive, current leads by 90. And if it's an RLC circuit, if it's a resonance in an RLC circuit, it's very similar to resistive circuit. Phase angle is going to be 0. Alright. Very good, Amar. Amar got 100. Hey, you got 100 of 70. Yes. Is this clear? Okay. So this is some important concepts that you need to know in alternating current. Now we will look at some important concepts in electromagnetic waves. Okay, just give me a second, students. Okay, so we will be looking at electromagnetic waves. So in electromagnetic waves, what do we have to look at? The first thing that you need to know is what is displacement current. So what is displacement current? You've all learned that the expression for displacement current is ID is equal to epsilon naught d phi by dt, where ID is actually the displacement current. But what is the difference between displacement current and normal current? So displacement current is like fake current. You don't actually have the flow of electrons. What is current? Current is a flow of electrons. But what is displacement current? There is flow of current, but there is no actual flow of electrons. So imagine you have a capacitor, okay? Yeah. So it's like fake current. So let's say, imagine you have a capacitor, okay? But you don't have electrons actually moving from one plate of the capacitor to the other, right? But the charges accumulate on each plate. But still there is a flow of charge, isn't it? It is not by electrons moving, but it acts like current because creates a magnetic field. It is not like a real current, but like virtual current. Electrons don't actually flow, but there is a flow of current. Okay, that is displacement current. All right. PDF is not clear. Numericals, I will tell you, let you know, okay? If I get the time to do a video on numericals, I'll definitely do a video on numericals as well. Don't worry. Okay? Alright? Yeah, most students lose marks on numericals, I know. Hi, Uday. MCQs, some MCQs I will teach in today's class. Okay, numericals and MCQs we will do. Alright? Yes. Okay. Yeah, so the displacement current, the formula is this much. This you already know. Now, what is the difference between conduction current and displacement current? Conduction current is due to the flow of charges, whereas displacement current, it is due to the change in electric field. So there is no actual electron flow. Just like I said, in two plates of capacitor, electrons are not flowing from this plate to this plate. But there is a change in electric field between the two plates. That is what is producing the current. Alright? Alright? Is this fine? Yeah? MCQ numericals only. Yeah, I will do a class of MCQ numericals only. Hopefully. Let's see. Okay? Because I have some other things as well. I'll try my maximum to do a class on that as well. Stay tuned. Okay? All of you subscribe to the channel. Like the video so we can keep giving you content of your choice. Whatever you ask, let's hope we can give you all that. Okay? Yes? Yes. Next is the expression for speed of electromagnetic waves in free space. So the speed of electromagnetic waves in free space is always given by square root of mu naught epsilon naught. What is mu naught? It is the permittivity of free space. Epsilon naught is mu naught is the permeability of free space. Epsilon naught is the permittivity of free space. Okay? Is this fine? Fine? Yeah. Okay. Yes. All right. Next is the expression for speed of electromagnetic waves in a material medium. So let's say V is the speed of the wave. So V will always be 1 by square root of nu by E, nu by epsilon. Okay. But nu is the permeability of the medium and epsilon is the permittivity of the medium. But with respect to C, you can modify this equation as C divided by square root of nu r epsilon r. Alright? Is this clear? So this is two ways in which you can write down the formulas. Okay. Now let's move on to. Is this clear to you, everybody? Yes, yes, yes. Did you all like the video? Have you all subscribed? Yes. Shirudas, PDF, always after the class, the PDF is always there under the video. So if you go to the video and go to the description, there will be a link to PDF. Okay, just click on that. You might have to join some channel, but you will get the PDF there. Okay? Yes? Mr. Gauss, numericals we will do, but in today's class we will do some MCQs after the class. Alright? Is this much clear? Can you all let me know? Can you put some fire emojis in the chat if this is clear? Quickly, students, quickly, can you put some fire emojis? Good afternoon, Nischil. I had my lunch. Did you have your lunch? Okay. Next chapter is ray optics. Ray optics is a very important chapter. In ray optics, first we will learn the laws of reflection. Okay. So let's say you have a mirror. All right. You have a mirror. On the mirror, to talk about the laws of reflection, I always draw an imaginary line which is perpendicular to the mirror. Okay. This imaginary line is called normal. What is it called? It's called normal. Now let's consider an incident ray. Okay. Incident ray is coming. It is hitting the mirror along the normal. The moment it hits the mirror, what happens? It reflects. It reflects. It reflects. Okay. Yes, Vaibhavi, this is for exam 2. Okay. Yes. Okay, Nishchit. You also had. Good. Alright. So what happens? The ray hits and it reflects. So the first law of reflection is that what all? The incident ray, the reflected ray, and the normal, they all lie on the same plane, which is the mirror. All these three lie on the same plane. Okay? Now, so what is the second law? The angle of incidence and the angle of reflection are equal. So what is angle of incidence? The angle between the incident ray and the normal. What is angle of reflection? The angle between the reflected ray and the normal. These two are equal. Okay. So these are the two two laws of reflection. Okay. Abhi says I look unhappy. I'm not unhappy, Abhi. In ray optics, you can't skip all derivations, but I will do only important derivations in today's class. That you learn. Easy derivations. Okay, that you don't skip. Monkey D. Luffy. Okay? Yeah? Okay? Oh, I look bored. I look unhappy. That's because I think it's an afternoon, no? And the weather is too nice. I mean, it's a sleepy weather. Maybe because of that. Okay, give me some energy then. Put something in the chat, all of you. Abhi says I don't have energy. Okay. Alright. Are you all with me in class? Yes? So these are the two laws of reflection. Hi Savita. What is this pink hand that you put? Does it have any meaning? Next is the sign conventions used in ray optics. Okay? Sign conventions are very important but very easy as well. So what are the sign conventions that are used? First thing, you have a mirror. Okay? So if you have a mirror, you always start measuring from the center of the mirror. Alright? Every measurement is from the center of the mirror. Now, any measurement from the center to this side, to the right of the mirror, is always positive. Okay? From the center to the right is always positive. Now, from the center to the left is always negative. Okay? Now, any measurement up is always positive. Any measurement down is always negative. Alright? Hemant Kumar, hi. Savita, hi. Habib, hello, hello. Hello, hello. Yes? Okay. So what are the three things that you need to know? From the center, any measurement to the right is positive. to the left is negative, upward is positive, downwards is negative. Alright? Is that clear? In some books, you'll see it depends on the direction of incident light as well. So if your light is coming like this, okay, if you're measuring from the center in the direction opposite to the direction of incident light, then it is negative. Same thing. You just need to know from the center to this side is negative, to this side is positive. More than enough. Okay? Alright? Yeah, those are the sign conventions that are used. Now we will look at some derivations. So some people hate this, but these are easy derivations. So I want you all to take a sheet of paper, pen and do it with me. Okay? Hi Chantrika. Hello. Okay? So all of you quickly go, take a sheet of paper, pen, do it with me. So I feel like you're all also doing it with me. No? Yes, yes, yes. Hi, hi, hi. Okay? Yes. Can we start? Shall we start? Yes. So first thing is a ray diagram. Okay? So all of you should learn to draw the ray diagram. So first thing what I will have, I have a mirror. Then what I will draw is, I will draw a principal axis. Okay? You draw a mirror and then a principal axis. Now the center of the mirror is point P. This is the focus. This is the center of curvature. Okay? Now what is center of curvature? Now if this is the mirror, this mirror is actually part of a circle, right? So the center of that circle is center of curvature. And focus is between the pole and the center of curvature. Okay? Now what I will do, my first ray is parallel to the principal axis. You can see it is passing through the focus. Okay? The first ray that's parallel to the principal axis is passing through the focus. Now what I'll do, I'll make an angle theta and theta. What is theta and theta? It is the angle between the angle of incidence and the angle of reflection. So here C is my normal. Okay, you can see C is at an angle of 90 with respect to the mirror. So theta and theta have to be the same. So if that is 2 theta, then this is 2 theta, alternate angles, isn't it? So if this is a point and I have an angle here, okay, shouldn't this angle also be the same? Alternate angles. Okay, see, like this. If you have something like this, these two angles should be the same. Okay? Fine? Yes, Rajit, I had lunch. Did you eat? Yes. Alright? So that is how this becomes 2 theta. Is that fine? So if this is theta, this will also be theta. See, again, alternate angles. So if that is theta, this is also going to be theta. So this is the diagram that you need to know. And I'll just draw a straight line here to make it a triangle. I'm very sorry for my pathetic drawing. That's why I always put figures that are drawn or printed. So you don't have to learn from my... Okay? Yes. Will the second exam be easy? Purvi, I don't know Purvi. I'm not part of the exam committee. The only thing we can do is prepare well. Okay? Let's see. Let's just hope that it will be easy, but you also prepare well. So whatever comes, it will be easy for you. Okay? Hi Rangaswamy. Sorry, Ragasway, is that your name? I'll just call you Savita. Hi Savita. Students, if I'm calling your names wrong, I'm very sorry, okay? Ma'am, NEET preparation is not there. NEET preparation will start. I will start it after I finish this exam 2 series. Next week onwards, NEET preparation will start. I want all of you to show your support for our NEET preparation. I want audience for NEET preparation, okay? Yes. Alright. Relation between focal length and radius of curvature is what we are going to find out. So you know this angle is theta. How is it theta? Alternate angles. Now let's take 2 triangles, okay? The first angle, I'll take tan theta. What is tan theta? With respect to this triangle. Okay? With respect to this triangle, what is it going to be? Tan theta would be opposite by adjacent, which is MD by CD. That is the first step. Tan theta is MD by CD. Very clear to everybody? Yes? Okay? Next, tan 2 theta will be what? Another triangle. I'll take it in different color. So the second triangle is this triangle. Okay? So what is tan theta 2 theta? Again, opposite by adjacent MD by FD, which is equation 2. Is it clear how I got equation 1 and 2? Everybody? Yes? Yes. Now what I will do, since the angles are approximately very small, see how it's small angles, no? So I can approximately write tan theta as theta and tan 2 theta as 2 theta. So removing the tan, what will I get? This will be theta is equal to MD by CD and 2 theta is equal to MD by FD. Is this clear? Yes? Okay. Now, what we will do, we will equate these two. So, equating these two, MD is there in both, so it cancels. So, then what can the relation between these two be? Can I write 2 CD is equal to FD? How can I write that? Because theta is CD and 2 theta is FD. So, that means 2 CD will be FD. Isn't it? Yes? So, 2 CD is equal to FD. From this I will get FD is equal to half CD. Now what is F into D? F into D is the distance between the focus and the pole, which is focal length. Now what is C into D? C into D is the distance between the center of curvature to the pole, which is radius of curvature R. Okay. So I already told you what is C. It is the center of a sphere, which makes the mirror. So the center to any side is radius. So now what is FD? FD is focal length. CD is R. So won't I get F is equal to R by 2? You also can get R is equal to 2F. It's a very easy derivation if you understand it. If you have understood this derivation, can you put some fire emojis in the chat? Or you can put yes in the chat. Quickly, students, can you let me know if this is clear? Any doubts for this derivation? Any doubts? Any doubts? Yes, this might come. Let's hope it comes. Himesh, how much will you get if you watch this completely? If all of these questions come, you'll get good marks. Okay? Yeah. Sapphire Soul, I've told so many times in this class that the PDFs are uploaded under the video. So if you go to the yesterday's class, under the description, there will be a link to PDF. Okay? Go. You might have to give some of your details. Join the channel. The PDF will be there. Okay? Yes. Is this fine? Yes. Yes. No. All revisions will come. Thank you, Desai. Desai has put yes. Others, is this clear? Why, Abhi? No. Okay? Okay, got it. Yeah, very easy derivation, right? Okay. Next. Nobody is forced me, Abhi. I am teaching by choice, see? Teacher by choice. Alright? Yeah. Yo. Yes, yo. Okay. Next is, we finished reflection. Now we will look at refraction. Okay? What is refraction? The first law of refraction. Even for refraction, see, in refraction and reflection, what is the main difference? The main difference is that in refraction, you have two mediums. In reflection, it is a mirror. So it's falling, it's reflecting. But in refraction, there's another medium and light goes, it passes through the medium, that's when it bends. So you need to have two mediums. So again, for refraction also, I will draw an imaginary line perpendicular to the medium, which is the normal. And then I have my incident ray. This incident ray has to pass through, but it might bend when it passes through. Alright? Okay? Yeah? Okay. So the incident ray and the refracted ray to the normal all lie in the same plane. Yeah? Do you see that? They all lie on the same plane. That is the first law of refraction. The incident ray, the normal and the refracting surface, they all lie on the same plane. Just a second. Notice I dropped my pen. Yeah. Sorry for that. Okay. Is this fine? That is the first law of refraction. Now, what is the second law of refraction? Second law of refraction is a simple law. Sin I by sin r is a constant. Which means, what is sin I? The angle of incidence. Sin r is the angle of refraction. Sin I is the angle between the incident ray and the normal. Sin r is the angle between the refracted ray and the normal. Alright. So, the ratio of the angle of incidence to the angle of refraction is a constant. Okay. And this is a constant for one particular pair of medium. So, sin I by sin r is a constant. This is also called as Snell's law, or it's sometimes also called as the sine law. Okay. They can ask you, what are the laws of reflection, or explain Snell's law or sine law. Alright. Is this fine? Got it? Got it? Yes? No? Are you all sleepy on a Sunday afternoon? Oh, students, by the way, happy Easter to all of you. Happy Easter. Yes. Okay. Next is total internal reflection. Now, what is total internal reflection? Total internal reflection is when refraction is not happening, which means the ray is inside itself. So, if you look at this picture, you can see that. What can you see? You can see something, no? Yeah. So, in the first case, there is an incident ray, okay? This incident ray, it is going to move from water to air. So, it is refracted, okay? Now, the angle of incidence is angle I, and this angle I is less than a value called critical angle theta c. Now, this value of critical angle can keep on changing for different mediums. So, let's imagine the value of critical angle for this is 40. So, angle of incidence should be less than 40. Only then it will be refracted. Now, what if angle of incidence is equal to 40, which is the critical angle? What is critical angle? It's just a particular angle for a medium. Okay. So, if angle of incidence is equal to that angle, then you can see that the ray is on the surface. Right? It doesn't move out of the surface nor into the surface. It passes on the surface. Alright. So, that is critical angle. The angle at which the refracted ray is parallel to the surface or the medium, the separation between the mediums. Okay. Now, the value of critical angle will keep changing for different mediums. Now, if the angle of incidence is greater than the critical angle, you will see that this angle, this incident ray is not able to escape the medium. Because its angle of incidence is greater than critical angle, it cannot escape the medium. So, what happens? It goes back inside the medium itself. It undergoes something called as total internal reflection. Okay? Is this clear? Yes? Okay? Yeah. Now, what you will do is, now where is this applied? This is applied in optical fibers. So, in optical fibers, if you have a signal, it keeps on going inside. It keeps on reflecting inside. So, this is because the incident angle falls at angle greater than critical angle. Okay. Now, what is critical angle? Critical angle for a given pair of medium is the angle of incidence in the denser medium for which the angle of refraction is 90 degrees. You can see here, the angle of refraction is 90 degrees. So, only if the angle of refraction is 90 degrees, then the angle of incidence is called critical angle. Now, when does the TIR take place? When the angle of incidence is greater than the critical angle. Is this clear? Yes? Yes, Sapphire Soul. Sapphire Soul has put yes. Okay, students. Now, let's move on. What is the next thing? Hi, Ganavi. Good evening. How are you doing? Okay. Next is the relationship between critical angle and refractive index. So, we already know from Snell's law, sin I by sin r is a constant. Okay. So, that can also be written as sin I by sin r is equal to the change in refractive index. So, this can be written as n2 by n1 instead of a constant. Okay. Now, let's look at this one here. So, yeah, from this, so what will it be? N2 sin R is equal to N1 sin I. So this is also another form of Snell's law. Alright. This is not clear, Desai. Is that what you mean? Can you just clear what you meant by no ma'am? Is it not clear to you? Yeah? Okay. So, right now what are you doing? Yeah, you have to find out the relation between critical angle and refractive index. So, what I will do on this formula, I will substitute some values. So, you know when angle of incidence is equal to critical angle when the angle of refraction is 90 degree. Isn't it? Is 90 degree. So, that means what is sin I? Sin I will be equal to critical angle which is N1 sin C. Now, it is going to be equal to N2 sin, how much is the refracted ray? It's 90. Isn't it? N1 sin C is going to be N2 sin 90. Now, you can see that it's going from some medium to air. So, what is the refractive index of air? It's going to be 1. So, this N2 is going to be 1. So, then I have N sin C is equal to 1 to sin 90. Why 1? Because it's moving into air. Now, what is sin 90? Is 1. So, 1 into 1 is 1. So, don't we get N sin C is 1? Yes. You get N sin C is 1. Right. So, what is sin C? Sin C is 1 by L. Is this clear to you? So, this is the relationship between critical angle and refractive index of the denser medium. Okay. Sin C is 1 by L. Is this clear? Hey, is my PDF not clear to you? Is it not clear? Can you all check the video and let me know? Is it not clear to you? Aishu, Uta. Someone's asking Aishu if you ate. Did you all eat? Yeah, it's clear. It's clear. Okay, it was just my internet problem on my phone. Okay. Is this clear? Yes, yes, no, yes, no. Clear, ma'am. Thank you, Ganavi. Thank you, Sapphire Soul. Thank you, Desai. Krish. Hi, Krish. How are you? Did you all eat? Are you all doing well? Yes. Okay. So, next one is what? The power of a lens. What is the power of the lens? The power is obviously the reciprocal of focal length. So, P is equal to 1 by F. Now, the SI unit of the power of the lens is diopter. Okay. So, P is equal to 1 by F. Very easy. Easy peasy. Right? Next, derivation. Where is my monkey? Monkey lover. Someone who asked me. Yeah, monkey D. Luffy. Are you here? You are. This is also an important derivation, but an easy derivation. Don't skip this. Okay? Nobody should skip whatever I'm doing in class because I'm doing most important things. Alright? Yes. And please wait because after this class we'll solve some MCQs. Okay. Next question. Find out the expression for equivalent focal length of two lenses in contact. Now we know that if you have one lens, the focal length is F, which is 1 by V plus 1 by U. Now we will find out the equivalent focal length if I have two lenses. Alright. So first what I will take? I will take refraction through lens L1. Okay. So now I'm going to imagine lens L2 is not there. Only L1 is there. So if only L1 is there, so imagine only L1 is there. Its focus is here. So it should be positive, right? It is towards the right, positive. Now image is going to be produced here, so that is also positive. But the incident ray U is from this side, so it's going to be negative. So 1 by F is equal to 1 by V1 minus 1 by U1, or it's just substitution of lens maker's formula. That also you can write. Okay? Alright? Okay? Now imagine only L2 is there. That means L1 is not the only L2 is there. What will its focal length be? 1 by F2 is equal to 1 by V2 minus 1 by U2. Now what is 1 by F? 1 by F is 1 by V minus 1 by U, isn't it? Now, if you combine these two, you will get 1 by F equivalent will be 1 by F1 plus 1 by F2, right? Because this is 1 by F1, this is 1 by F2. So these two added together will give you 1 by F, isn't it? So now what is F equivalent? F2 plus F1 by F1 F2. Now taking the reciprocal, F1 F2 divided by F1 plus F2. This is 1 by F, this is F. Is this clear? Super. Are we all on the same page? Yes? Paka clear? Can you all let me know in the chat if this is clear to you? So you only have to do two things. First, ignore lens 2 and write the equation for lens 1. Then ignore lens 1 and write the equation for lens 2. Alright? Yes? And then what happens? See, the general formula is 1 by F is 1 by V minus 1 by U. So what is 1 by F1 plus 1 by F2? It is equal to 1 by F equivalent. Alright? Yes, yes, yes. Can I have some fire in the chat? The chat is so dead today. Where are you all? Students, go share this link to all your friends and ask them to join. The chat is so dead today. Where is everybody? Now, your energy is what keeps me motivated. Okay, Desai, thank you. Alright, now let's move on to the next chapter, which is wave optics. Hi, Kritik. Hello, hello. Go call your friends also. Ask them also to join. Yes. Okay, next is chapter 10, which is wave optics. Wave optics is also a very important chapter, but a very easy chapter as well. Okay? Yes, let's start. Hi, Neha Gowda. Hello. Hi, hi, hi. Yes, let's start. Okay, next is reflection of plane wavefront using Huygens principle. Okay, so what we are going to do is, what is Huygens principle? Someone tell me in the chat, what is Huygens principle? It just states that every point on a wavefront acts as a source for a secondary wavelet. Now, first thing you need to know in this chapter, what is wavefront? So imagine you have a stone that is dipped in water. Okay, I go to a river, I drop a stone in the river. What happens? Around the stone, you will see ripples. But some of you might think that these ripples are waves. But no, these ripples are not waves. Then what are these ripples? These are something formed around the stone. What are they? So they are wave fronts. Okay. So from every stone, you can see there are waves that are going to be produced in all directions. Okay. Waves are a little more neat, but not this bad. Okay. So there are going to be waves produced in all directions. Now what I will do is not what I do, but what a wavefront does is it takes points on each of these waves that are in same phase and are the same. So each of these points on every wave is taken and then joined together to form a wavefront. So that's how you get a circle. So the circle, okay. So the circle is basically a wavefront. The first ripple is a wavefront, which is a collection of thousands of waves. Do you understand that? That is a wavefront. So Huygens principle states that now this first wavefront that you have, every point on this wavefront acts as a source for secondary wavelets. Okay. So the second ripple comes from the first one. So imagine this is the first wavefront. Okay. 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 Now imagine this is the first wavefront. Alright. Now from this wavefront, what happens? These rays, it produces secondary wavefronts. Okay. Excuse me, students. And this will form a secondary wavelet. Is this clear? Okay. Can you just give me a second? And I'll just, yeah, 1 second. Very sorry, students. I just got a cold. Okay? Yeah. So what were we discussing? Secondary wavefronts. So first wavefront is the first ripple that you have. Okay? Now each point on the first ripple acts as a source for secondary wavelets. Is that fine? Yes? No? Are you all there? Are you all sleeping? All those who are sleeping in class, please put sleeping in the chat. Yeah? So that is a wavefront. Now, first thing that we're going to learn in this chapter is the reflection. Okay? The reflection of plane wavefronts. So what is a wavefront? A wavefront is a group of waves. It's not a single wave. So many waves joined together is a wavefront. Now, if you have straight waves, okay? Imagine you have so many incident rays like this. I can draw a wavefront for this also. How will I draw it? I'll just draw a line that joins all of these at the same phase. So this is my first wavefront here. I can draw many wavefronts. Alright? So a wavefront is a group of waves. Is that clear? Ma'am, PDF. Students have, see, PDF is always there under the video. You just have to go to the description of the video and download the PDF. But this class PDF you will get after this class only because I have to upload it. Alright. Okay. Now first, reflection of plane wavefront using Huygens principle. So let's look at the figure. So what is happening here? So here you have a plane wave. Sorry, you have a surface. Okay? Wavelet is just wavefront, same thing. Okay? So look at this figure here. So first thing, you have an incident wave A. Okay? It's falling on the mirror or the reflecting surface. Now you can see that B is coming from a far off point. Right? B is coming from a little more far point. So B will reach the wavefront after some time. So A has all, so these waves are coming like this. Okay. So this is the surface. A already reached, B only reached here. A reached here, B only reached here. So by the time B reaches this point, A would already be reflected. Okay. So A will hit, A will reflect. But B has not hit yet. So B has not reflected yet. Now, I will draw a wave front joining the two incident rays. Okay, remember very carefully, the wavefront that I am drawing is going to join the two incident rays. So this is the first incident ray, this is the second incident ray. So I am going to join them and this is going to be my first incident wavefront. So what is this central green line? It is a line joining the two incident rays. So that is the incident wavefront. Now if I have many more rays, all of those will fall on the incident wavefront. Is that clear? Yes? Yes? Clear? Okay? Now what I will do is, I will draw the reflected wavefront. So what are the reflected rays for me? What are the reflected rays? Yeah? Let's see. What are the reflected rays? The first reflected ray is this one. The second reflected ray I have not drawn yet. So it's going to be reflected from this point. Okay. So the reflected wavefront, I will draw it like this. So this is the right line, the wavefront joining all the reflected wavefronts. So here I have my incident and reflected wavefronts represented by the green and yellow lines. Okay. Yes. What happened, Mohammed Tafiq? Is this clear? Okay. Alright. So now, what I will do? What I will do is, I will look at the angle of incidence. So, angle of incidence is the angle between the incident wavefront and the plane. Angle of reflection is the angle between the reflected wavefront and the plane. Not the incident ray, not the reflected ray, but a group of incident rays and reflected rays form the incident wavefront and the reflected wavefront. Okay. So, according to Huygens, the angle of incidence and the angle of reflection have to be equal for wavefronts as well. Alright, just not for waves but for wavefronts as well. Angle I and angle R are equal. Is this clear? Okay. Next, we will do a derivation. A quick, easy, simple derivation. So this derivation is for what? For your exam. So this is a derivation to find out Snell's law of refraction, or to prove that refraction of a plane wavefront using Huygens principle. Okay. Hi, I'm not able to pronounce your name. Muichiro? Yeah? Yes. Ma'am, how to download? You can just go to the channel. You'll have to join the channel. Okay. In the description, you go to the channel and then you can access it. You can't download it. Alright. Hi, Archana. Hello, hello, hello. Yes. Are you all ready for a derivation? If you are ready, put ready in the chat. I want some energy. All of you. If you are ready for the derivation, please put ready in the chat. So we can start. This is a derivation for Snell's law of refraction. Puneet is only saying hi to Archana. What about me? No hi for me. Let's start. Okay. Yes, Ganavi is ready. Sapphire Soul is ready. Nobody else is ready. Where are the others? Yes. What are you all up to on Sunday? All of you are at rest or in motion? Let's go, ma'am. No, you're not late. You're on time. Okay? Yes, Archana is also ready. Superb student, super. Himesh, you can't score a centum by this because I'm not going to do numericals and I'm doing some MCQs, but you need to know numericals as well. But this is very important things. For a centum, you have to learn the whole book. Okay? Yes? Yes, Habib, Desai. Thank you for your energy. Okay. So let's start. Oh, you already got 43 out of 70. Very good. So to get more marks, you'll have to do numericals as well. So, okay? Alright? Yeah. So first then let's understand the figure. So what was the previous figure? For the previous figure, what happened? We had a surface. Okay? We had a surface. So there was an incident ray and the incident ray was reflected. But now you can see it is refracted. So this is the incident ray. Okay, these two are the incident rays and they are both refracted. Alright? This is fine. Okay. Now what I will do? I will draw the wavefronts for the incident and the refracted. Okay. So the incident rays together, this is the wavefront. The refracted rays together, this is the wavefront. Alright. So what is a wavefront? A line joining the rays. The rays have to be at the same phase along the line. Okay. As I said, in this chapter, we'll be looking at wave fronts, not waves. So what is the angle of incidence? It will be this angle, the angle between the incident wavefront and the medium. What is angle of refraction here? This one. Okay. Now, we also know that the first ray, it is incident at V1t. The distance is V1t. Okay. Now, this second ray is refracted at a distance of V2t. V2 is the speed and t is the time. V2t. Okay. This is the figure. Is the figure clear to all of you? Yes. Is this figure clear to everybody? Yeah. Let's move on. So now BC. What is BC? What is BC? BC is this. BC is V1t. Okay. What is AD? AD is V2t. Alright. So this is why did I take these two? Because these are the distances between the incident wavefront and the refracted wavefront. Alright? Alright? Yeah. So the incident wavefront and the refracted wavefront both have distances V1t and V2t. Now what I'll do, I'll take two triangles. The first thing I'll take is taking sine I. Okay. So sine I. So what is sine I? Sine I, this is the angle. So it is definitely BC by AC. So this is a triangle. BC by AC is sine I. So what will sine R be? Sine R is going to be AD by AC. So you have to know which angle you are taking. Okay. AD by AC. Now if I do sine I by sine R, what will I get? AC cancels. So what will I get? I will get BC by AD. Now what is this equal to? BC is V1t and AD is V2t. So this is going to be equal to V1 by V2. Isn't it? So we already know from Snell's law, sin I by sin R is N2 by N1. So now I know N2 by N1 is V1 by V2. Right? That is what we have proved here. N2 by N1 is V2 by V1 by V2. Okay? Happy Easter, Abhijit. Okay? I'll explain again this side. Yes. Okay. So I will explain this figure once again to those of you who haven't understood. So what we are going to do is, you have two incident rays. Okay. So you have two incident rays. Yes, I will explain. You have two incident rays. Okay. These two incident rays are refracted, and the two refracted rays are this much. Is this clear? Now I will take a wavefront, which is a line joining my incident rays at the same phase. So my line is this one. So the angle between the incident wavefront and the plane is angle I. Now I will also draw another line for my refracted wavefronts, and this is angle R. So the angle line joining both my refracted wavefronts is R. Okay? Is this much clear? Now what I am going to say is, see, now, okay, so one thing that I didn't explain earlier, I'll explain it now, is that you can see this incident wavefront. This incident wavefront is going to reach the plane or the medium in how much distance? This much distance, which is V1t. Okay, so this is the medium, this is the incident wavefront, this is going to reach here. With how much distance, speed into time, it is V1t. So this distance is V1t. Okay, is that much clear? So, incident wavefront will reach the medium with a distance of V1t. Now, similarly, the refracted wavefront. Okay, how do I keep my hand for that? This is the medium, this is the refracted wavefront. Okay, this refracted wavefront traveled a distance of V2t. So, from the medium, it has reached here. See, this is the, do I look funny? Yeah. So, if this is a medium and this is the refracted wavefront, the refracted wavefront reached here. From the medium, it reached here, right? It traveled a distance of V2t. So this much, it traveled a distance of V2t. So V2t is the distance the refracted, this one traveled. V1t is the distance the incident wavefront is going to travel. Is this clear? Karthik, is it clear? Yes? Is this clear? Can you let me know in the chat if this is clear? Yes? No? Yes, no. Students, how was your KCET exam? Please let me know how your KCET exam went. All those who were there for the KCET sessions. Was it good? Clear? Okay. Good. Wonderful. Okay. So let's move on. It was moderate. Yeah, physics is always like that. It will not be easy, but it will be moderate. Did you all check your scores? Will you all score well? Not bad, Ganvi. Okay. 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 Fine. Okay. No problem. So is this clear to you? Yeah. If this derivation is clear, that we found out the relationship between speed and change in refractive indices for refraction of wave fronts. If this is clear, can you put some fire in that cat? Oh, you're expecting 40 plus. Well, good enough. Good, good. Very good. Very good. Yes, shall we move on? Shall we move on? 57. Archana is expecting 57. Very good, Archana. Superb. Yes. Okay. Next, what we're going to discuss is interference of light. What is interference of light? Interference of light refers to the modification in the distribution of energy. So, when there are two light rays, so what happens? There are two light rays. These light rays come, they interfere together at a point and they superimpose. That is called interference of light. You will get 98. Wow. Super. Okay. That is called interference of light. Now there are two kinds of interferences. Constructive interference and destructive interference. What is constructive interference? So if this is your initial ray, okay, and the second one is also along the same phase, they will superimpose and you will get a big one. Constructive interference. Now what is destructive? For destructive, again this is your incident ray, but the second I1 and I2, two rays have to come and superimpose, but the second ray is like this. So they superimpose to give you nothing, a dark line. So this is destructive interference. Okay. The first one is constructive. The second one is destructive. Now you have to learn the formulas for path difference, phase difference for both constructive and destructive. Now you know what they are, right? What are the formulas? 2n pi and then delta is equal to n lambda. For destructive it becomes 2n plus 1 pi and delta is 2n plus 1 lambda by 2. These formulas you have to learn. Alright. Okay. Is this fine? Yeah. Yes, yes, no, what's happening? Okay. I have a small nose cold issue. So that's why I have my tissue. Alright. Yes, no. Can I have some response in the chat? Where is your energy? Where are all my students? Hi, Tahasina. Hello, Tahasina. Welcome to the class. Okay, Desai. Yeah. Yes. Okay. Next is the difference between interference and diffraction. What is interference? In interference, all the bright fringes are equal. In diffraction, all the bright fringes are not equal. Okay. So, in interference, the number of fringes observed, you can see many fringes. But in diffraction, you can see very few fringes. In interference, all dark fringes have zero intensity. In diffraction, the intensity of all dark fringes is not zero. The width is same, the width is not same. Okay? I've already... Yeah, maybe. I didn't eat ice cream. I just bought it from somewhere. I don't know. When you eat a lot of ice cream, do you get it? Okay? So what is diffraction? What is diffraction? I mean, diffraction fringe, how will you get the diffraction fringe? It will always look something like this. So you'll have a central bright fringe and then the intensity will keep on reducing. But for interference, it will be the same throughout. Okay? Is this fine? Yes? Next is about Polaroids. Okay? So what are the uses of Polaroids? 3D pictures, optical properties of metals, sunglasses, vehicle windows, all of these help us get Polaroids. Alright? What are Polaroids? Polaroids it just reduces the amount of intensity reaching your eye. So if you look at the sun with your bare eyes, you will not be able to look. But if you use a sunglass, you can actually stare at the sun. How? Because the sun has a Polaroid. Polaroid is a material that has polarization property. So it cuts one set of light rays and only the other set will reach your eyes. Is that clear? Okay? Yeah, Ganavi, today there's nobody voting for CSK and RCB. Yes, I missed them. Did you all like the video? I forgot to say that as well. Please go like, share, subscribe. Okay. Alright. Next. Next is a method for producing plain polarized light. What are the different methods? You can produce it by reflection, refraction, and double refraction. So these are the three methods by which you can produce plain polarized light. Alright. Is it fine? Any doubts? Uh-huh. Yes? No? Okay. Okay. What is fringe? Someone has asked me what is fringe. So fringe is basically just the light and dark bands. Okay, the output when diffraction or interference happens, the output has light and dark intensities, right? They're called as fringes. All right. Is that clear? Anything else? Any other doubts? Is it clear? Kartik, I think your name is Kartik, right? Yeah. Mm-hmm. Okay. Next, Mal's law. Hey, what's happening between Ganavi and I can't read your name. What is this, students? Listen to my class. Yeah. So, what is Mal's law? It actually describes the intensity of polarized light transmitted to an analyzer. So, imagine you have an analyzer and you have polarized light coming. So, after it passes through it, the intensity will be I0 cos square theta. Okay. So, after it passes through the analyzer, the intensity varies as the square of the cosine angle times the intensity. That's all. A very easy law. Okay. Okay. So, I naught is the intensity of the unpolarized light. I is the intensity of the plain polarized light. Theta is the angle between the polarizer and the analyzer. Is that fine? Next chapter is dual nature. Okay. Next chapter, dual nature. Are you all ready for dual nature? Quickly tell me, are you all ready for dual nature? Yes, no, not here, ma'am. What are you doing, ma'am? Where are you all? Where are you all? Put some fire in the chat, students. If you're there, put some fire in the chat. Where are all your friends? Yesterday I had more students. Where did all of them go? Yes, Archana's here. Okay. In dual nature, the first thing that we need to know is the types of electron emission. So there are different kinds of electron emissions. There is thermionic, photoelectric, field and secondary. Okay. So in all of these cases, electrons are emitted. But in the first one, electrons are emitted because of heat. Okay. Okay. So in thermionic emission, electrons are emitted because of heat. In photoelectric emission, electrons are emitted because the incident light comes and hits it and removes the electron. And in field emission, what happens? A strong electric field ejects an electron. In secondary emission, a high energy particle emits the electron. Very easy. Okay. Now we will look at some observations of photoelectric effects. So you actually, for your exam point of view, the headings are more than enough, but then you need to know what they are, right? That's why I've put a small explanation as well. So photoelectric effect occurs instantaneously. There is no time delay. So the moment light falls on the surface, an electron is ejected. But the light does not fall and wait. Okay, let the electron eject after 20 seconds. I'll keep a timer. No, it's an instantaneous process. The moment electron falls on it, it is ejected. That is why it is called instantaneous emission. Next is threshold frequency. Only if the whatever is incident on it, only if it is above the frequency of the threshold, That is when the electrons are emitted. Otherwise, no electrons are emitted. Whatever intensity of ray falls, the frequency should be greater than V naught. Okay. Next is intensity versus current. So the photoelectric current is directly proportional to intensity. All of these are very important. Okay. Very, very important. So photoelectric current is directly proportional to intensity. Now, how is frequency and kinetic energy related? The maximum kinetic energy increases with frequency. Alright. Now, what about stopping potential? So, photoelectric current will become zero. One negative potential, that is called as the stopping potential. So, stopping potential is a potential at which the photoelectric current becomes zero. Is that clear? Okay. Next is frequency versus stopping potential. What is the relation? They are directly proportional. Okay. Frequency and stopping potential, they are directly proportional. Is this fine? Okay. Next is Einstein's explanation of photoelectric effect. Alright. So what's Einstein's explanation of photoelectric effect? So Einstein explains that based on the quantum nature of light. So what Einstein said that, light, okay, if you have a light ray, okay, this light ray has packets of energy. Okay, there are so many packets of energy that this light ray has, and each of the packet is called a photon. Alright, and each of the photon has an energy is equal to h nu. So if you have a ray of light coming, this ray of light is full of packets of energy. Each packet is one photon which has an energy h nu. Alright, now when this photon comes and strikes a metal surface, what happens? The energy is used for so many different things. First, the energy is used to eject an electron. The second, the energy is used to transfer as kinetic energy. So the total kinetic energy is what? H nu minus H nu naught. H nu naught is the minimum energy needed to eject an electron. Okay. So kinetic energy will be equal to the energy of the system after ejecting an electron. That is H nu minus H nu naught. So half mv square is equal to H nu minus H nu naught. Alright. H nu naught is the minimum energy to eject the electron. So the moment the radiation comes and falls, it takes some of the energy to emit the or to break the electron. Okay. What about electron? I didn't get you, dear. What is it? What about electron, Asin? What are you talking about? Is this clear? Einstein's explanation for photoelectric effect. Is it clear? Yes? No? No. Students, please don't, get offended by things in the chat. You don't have to mind that. Listen to the class. Okay? Yeah. Now, next is key points from Einstein's explanation. So, from this explanation, what are the key takeaways? The first one, I already discussed that it is instantaneous. So, the moment the photon goes and hits, the energy is taken and an electron is ejected. Now, if nu is equal to nu naught, then there is no kinetic energy. Why? Because kinetic energy is what? H nu minus H nu naught. If nu and nu naught are the same, then all the energy is used up to remove the electron. There is no kinetic energy. Alright? Ma'am, no. This is not clear to you. Is this not clear to you? Can you tell me? If photoelectric is not clear to you, can you put no in the chat so I can explain it once again? Apu and Archana, can you confirm if we are talking about photoelectric effect or not? Yes, I am free. What happened? Yes. Can you let me know? I'm waiting for your reply. I'm not able to see your response. If you're saying something or not. Once again. Okay. Alright. Students. So what is Einstein's explanation of photoelectric effect? So what Einstein said that is light. Okay. So we know light is a wave. Now what Einstein said is light, it comes and it falls on something. Alright. Okay. So this light is made out of small packets of energy. So this full light ray has so many packets of energy, and each packet of energy is called a photon. Okay, what is photon? A light ray is made out of so many photons. Just like your body is made out of so many atoms, a light ray is made out of so many photons. Each photon will have an energy of h nu. Okay, each photon will have an energy of h nu. Okay, now what we have is this is a metal. Okay, metal. So this photon, light ray which has photon, this is going and coming and hitting the metal. So once it hits the metal, what happens? Photon has an energy of h nu. This energy is used up by one electron to get ejected from the metal surface. Okay, so the amount of energy that the electron takes to eject out of the metal surface is h nu naught. So energy comes in, out of which h nu naught is used up by the electron to remove itself from the metal surface. Now there is some energy remaining. That remaining energy is basically the kinetic energy. So what should the kinetic energy be? Kinetic energy should be the total energy is h nu, the energy of the coming photon. That minus the energy that the electron took to move out, which is h nu naught. That is kinetic energy. That is half mv square is equal to h nu minus h nu naught. Is this clear? Archana and Sakina, Sapphire Soul, can you let me know if this is clear to you now? Yes. So whatever energy comes from the photon is used up in two things. One, to remove the electron, which is as h nu naught. The rest as kinetic energy. Is it clear now? Yes, no? Yes, no? Yes. Okay. Super. Okay. Now, based on this, we will make some assumptions. So, these are the key points from Einstein's explanation. First thing Einstein said, it's instantaneous. So, the moment the photon comes and hits the metal, an electron is emitted. Okay, it's an instantaneous process. Now, if V is equal to V naught, then what happens? The total energy coming is h nu. So, all of this h nu is used up by the electron to eject out. So h nu naught and h nu are the same. So then is there any energy left as kinetic energy? No. Kinetic energy is going to be 0. Okay? No problem here. Alright? Now, if nu is greater than nu naught, what does that mean? So the photon has a very high energy. It comes, hits the metal and it emits an electron. But it has a lot of energy. Very little is taken to emit the electron. Then what does it mean? It has a lot of kinetic energy as well. So kinetic energy becomes greater than 0. Why? Because h nu is greater than h nu naught. So even after electron is emitted, there is still energy remaining, which will be kinetic energy. Now what happens? If h nu is less than h nu naught, what happens? Then kinetic energy will be less than 0, because the photon itself has no energy to eject the electron. So there will be definitely no electron coming out nor kinetic energy. Both will not be there. Okay. So if it's above the threshold frequency, which is the minimum frequency required to emit the electron, photoelectric current is proportional to intensity. Alright. Now, maximum kinetic energy is also directly proportional to the frequency. So if the frequency is very high, you will have a lot of kinetic energy. Alright. Is this clear? Can you let me know, students? Key points from Einstein's explanation. Is this clear to you? Yes, no, yes, no. Yes. Shall we move on to the properties of photons? Okay. The properties of photons. Thank you, Abhijit. So first thing is that the rest mass of a photon is 0. Yeah. When a photon is at rest, its mass is 0. They always travel with the speed of light. What are photons? Photons are particles inside light rays. So if the light ray travels with the speed of light, photons will also travel with the speed of light. They move in straight lines. See, a light ray always moves in a straight line. If you have a torch and you keep something in front, the light does not bend and go this way. It always passes straight. So photons will also travel in a straight line. Photons are electrically neutral. So photons are not going to be deflected by electric and magnetic field. And the energy of the photon already discussed, E is equal to h nu. Because photons are neutral, it is not going to be deflected by electric or magnetic field. Okay. Kritik wants me to explain the fourth point. See, fourth point is if V is less than V naught. Okay, what does that mean? What is V? HV. What is V naught? HV naught. So HV is the energy of the photon coming. So the energy of the photon coming is very less compared to the energy required to remove an electron from the metal surface. See, this photon brings energy and this energy is used up to emit an electron and to have kinetic energy, right? But if the coming photon itself has very little energy, the energy of the coming photon is less than the energy required to emit an electron from the metal surface. So then what happens? Then the electron cannot be emitted from the metal surface, nor can kinetic energy be there. Isn't it? Because what is kinetic energy? Kinetic energy is h nu minus h nu naught. But h nu is very small compared to h nu naught. So h nu naught is not possible because there is not that much energy to emit the electron. So there is no kinetic energy also. Is that clear? Kritik, can you tell me if it's clear? Hi Telugu Gaming. Hi. Yes. Is it clear, Kritik? Still not clear? Can you let me know? Okay. Next is de Broglie waves or matter waves. Now, according to de Broglie was a very famous scientist. So, according to de Broglie, all moving particles have wave-like properties. Okay, clear. Okay, every moving particle has wave-like properties. And they are called matter waves or de Broglie waves. Alright? Is that fine? Okay, the wave nature becomes significant when the particle is very small. Okay, so every particle has a wave-like property and it has a wave-like property only when they are very small, like electrons. So a group of electrons will obviously act like a wave. Is that clear? Okay. Now, next is the expression for de Broglie wavelength. Now, in terms of mass and velocity, the wavelength is h by mv. These are some very important equations. In terms of momentum, P is equal to mv. So this will become h by p. So this mv will be p. Now in terms of kinetic energy, what will it become? H by root of 2m k. Now in terms of voltage, accelerating voltage, what will lambda become? H by root of 2m qp. Okay? De Broglie waves. See, it's very easy. So according to de Broglie, he is just saying that any moving particle that is small, very small, like a proton and electron, they act like waves as well. So what have we learned? We have learned that protons are particles, electrons are particles, but de Broglie says that they act as waves as well. These waves are called matter waves. And for them to act as waves, they should be small. So big particles will not act as wave, but very small particles will act as wave. That's all that you need to know. Okay? Yes, formulas play a very important role in physics, gaming, FF. Alright? Okay, so these are the expressions for de Broglie wavelengths. Okay, some equations that you need to know. The derivations of these are not that much important, but you need to know the formulas for these. Okay? No problem, Archana. You don't have to thank me for explaining. It's my duty to explain it to you. So that's all about dual nature. Now we will look at atoms. Okay? We'll quickly look at atoms. Now, first thing in atoms that you need to know is a very famous alpha scattering experiment. So what is the alpha scattering experiment? You have a gold foil. Now you have a source. The source has an alpha source. What is an alpha particle? An alpha particle is a particle with 2 protons and 2 neutrons. Okay? What is it? It has 2 protons and 2 neutrons. It is similar to a helium nucleus. Not a helium atom, but a helium nucleus. What is a nucleus? A nucleus has only protons and neutrons, no electrons. Okay, so an alpha particle is similar to helium nucleus. Alright, is that fine? So this alpha is going to pass through a gold foil. It's going to pass through a gold foil. So let's see. As the alpha reaches the gold foil, you can see three things are happening. So many things are happening, but three are the main. Either it passes through the gold foil, or it bounces back, or it deflects at an angle. So the alpha particle that comes, it either passes through the gold foil, or it deflects back, along the alpha itself. Now you can see these three things happening. But why do you think these happened? That was the alpha scattering experiment. Okay? So what is the first thing? First thing we take, there are atoms in the gold foil. Gold foil is full of atoms. Now, most of the alpha particles passed through. It proved that most of the atoms in the gold foil are empty. Most atoms have empty space. Okay, that is why most of the gold foil particles were able to pass through. Some of them were deflected at angles because they hit the nucleus of the gold foil. Why? Alpha is positive, nucleus is also positive. So if the alpha goes and hits the nucleus, positive repel, that's how they deflected. Now, some of them bounced back. That is when they were exactly hitting at the nucleus. Some deflected at angles when they were near the nucleus. Okay. So even if it's near the nucleus, it will be deflected, right? Positive, it should be deflected. Okay, you can see very few particles were deflected because the nucleus is very small. Most of the particles passed straight through because most of the atom is empty. Alright, so these were the conclusions from alpha scattering experiment. Most alpha particles passed straight through. Some were deflected at small angles, some bounced back. The small angles were because they were close to the nucleus. They bounced back because they hit exactly at the nucleus. Most of them passed straight because most of the atom is empty space. Is this fine? So this is the structure. You have an alpha source, you have a gold foil, you have a detector. So you can see some pass through, some deflect, some bounce back. Okay? Is this clear? Yes, no, can I know in the chat? Yes, students, is this clear? Have you all liked the video? All those who are watching, please go like our video, subscribe to our channel so we can keep giving you lots of amazing content. Yes, Telugu Gaming. Tell students, focus in the class. Yes. Okay. Now, yes, that's... Next is a postulates of Bohr's atomic model. So after Rutherford's alpha scattering experiment, Bohr gave an atomic model. So that is when he said in the center there is the nucleus and then there are electrons revolving around them and all that. Okay. So first thing that Bohr said was electrons move around the nucleus in stable orbits. Okay. And they don't radiate energy when they're in their stable orbits. It's like when you're at home, you're comfortable. You don't have to prove anything to anybody. So you just live your life. Same thing, an electron in its own orbit does not have to radiate any energy. It just moves in its own orbit. Next, the angular momentum of an electron is quantized. So every electron will have an angular momentum which is nh by 2 pi and it will depend on in which orbit it is, which is n1, 2, 3. Okay? Next, energy emission or absorption. An electron emits or absorbs energy when it jumps between two energy levels. So let's say these are two energy levels. There is an electron here. Okay? Okay, there is an electron here. This electron gains energy from something, some radiation falls on it. The electron gains energy, it moves to a higher energy level. Now it is here. But once it reaches the high energy level, it realizes it cannot stay there for a long time. So what happened? It comes back to its home. Okay? It's like you go for a trip and you're spending your holidays, you're enjoying there, but then you realize you don't have enough money to stay there forever. You come back home. And on your way home, you spend all the extra money you have. Similarly, what does the electron do when it comes back home? It emits all the extra radiation it has. It emits all the extra energy it has. Okay? So it takes a lot of money. It goes to the next energy level. It enjoys some time there, but then it realizes it cannot stay there. It comes back. On the way back, it sends away all the energy. So it absorbs a photon and it emits a photon. Is this clear? Hi, Singer. Alright. Now the energy difference will be E2 minus E1, which is h nu. So h nu will be the energy of the radiation it emits. Okay? Is this clear? Yes. So that is the energy of emission or absorption. Okay? Yes, no, yes. Yes, yes, no. Okay? Yeah. Next is the drawbacks. What are the drawbacks of Bohr's theory? The first one, it is applicable only to hydrogen-like atoms which have single electron. It was unable to explain the fine structure of spectral lines. Okay? It was not able to explain Stark effect or Zeeman effect, and it does not consider the wave nature of electrons. Alright? You don't have to learn these in detail, you just have to know all of these. Alright? Next is a derivation. Something most people hate, but yeah, let's do it. It's as I always say, the derivations I do, very easy derivations. Yeah? So if you're all ready for a derivation, can you put some fire in the chat? Everybody in class, please put fire in the chat if you're ready for the derivation. Fire, fire. I want some energy now, students. Can you put some fire? Yeah? Yes, I want you all to go smash the like button and put some fire in the chat if you're ready for doing derivations. Yes. Ma'am Pakka, yeah, someone who has watched my KCET series. Hi Sam, San. Okay, ready? Yes. Others, yes. Superb, superb. Yes. Okay. I want more fire. This is not the energy that I have in my class. Where are my students? Paka question, yes. Paka question, yes. Yes, she's putting bombs or crackers. Okay, so let's start. So we're going to find out the energy of an electron in an orbit of Bohr, in one orbit. So total energy is definitely kinetic energy plus potential energy. Okay. Now, we also know that the two forces, when an electron moves, okay, this is an orbit. When an electron moves in an orbit, the two forces acting on it, first is centripetal force to the center, and then the electrostatic force of attraction, the electrostatic force between the nucleus and here, right? So, how will I equate them? What is centripetal force? mv square by r should be equal to 1 by 4 pi epsilon naught z square by r. Only then the electron can rotate in a circular orbit if the centripetal force and the electrostatic force are equal, right? Isn't it? Now what I will do, I will multiply both sides by r. Okay. So what happens? mv square will be 1 by 4 pi epsilon 0 z square by r. R square term is gone. Now kinetic energy is half mv square. Now what is half mv square? Half into m into v square, which is mv square is already, okay, I'll write it. What is mv square? mv square is 1 by 4 pi epsilon naught z square by r. Now what will half mv square be, which is kinetic energy? mv square into half, which is 1 by 4 into half, 1 by 8. 1 by 8 pi epsilon naught z square by r. Alright. Now what is potential energy? Potential energy, we already know it is what? Minus 1 by 4 pi epsilon naught z square by r. Okay. Yeah. So I have kinetic energy, I have potential energy. What is total energy? Kinetic energy plus potential energy. So let's add that. Let's add kinetic energy and potential energy together. So what will it become? It will become 1 by 8 pi epsilon naught z square by r plus, but potential energy is negative, so minus 1 by 4 pi square epsilon naught z square by r. Now I'll take all the common terms outside. So what remains? The only thing that remains is 1 by 8 and 1 by 4. So 1 by 4 I take outside. The only thing that remains is 1 by 2 minus 1 into 1 by 4 pi epsilon naught Z square by R. Is that fine? So if you do the math, you will get minus 1 by 8 epsilon naught Z square by R. Alright. Now what I will do is, I will substitute the value for R. Oh, you're not able to see it. So what is the value for R? This is a value that you need to know. 4 pi epsilon naught n square h square by m e square z. Okay. So I will substitute that value of R. So instead of this R, I'll write down this value. So this becomes 1 by 8 pi epsilon naught z square divided by 4 pi epsilon naught n square h square divided by m e square z, and then when you do the math, you will get this answer. Okay, you might not have been able to do it with me because it's a little long, but you will definitely be getting it if you try to do it alone. Alright, so now if it's for hydrogen atom, Z is 1, so you can just take Z as 1, you will get this formula. Now what does the negative sign show? The negative sign shows that the electron is bound to the nucleus. It is not moving out, it is bound to the nucleus. Alright, is this clear? Okay, so this is the energy for electron in the nth orbit of hydrogen. Okay, now let's move on to the energy level diagram of hydrogen. So this is the energy level diagram of hydrogen. So you can see that from any excited state, if the energy is coming and falling on the first ray, on the first band, it's called Lyman. From any higher energy level, if it's coming and falling to n is equal to 2, it's called Balmer. So any high energy, if it's falling to 3, is Pascal, and then bracket, and then Fund. Okay, so whenever you have n is equal to 2, it means from any high energy level, it's coming and falling to n is equal to 2. N is equal to 4 means from 5, 6, 7 and all, it's coming and falling to n is equal to 4. Okay, now the hydrogen spectral series and their regions. So a Lyman series is usually found in the UV region. Balmer is usually visible light. Pascal is usually IR. Bracket is usually IR. Fund is also IR. Alright. Now there's a question. Quickly tell me the answer. In which region of the electromagnetic spectrum does each of the following hydrogen spectral series lie? So answer I already gave you. For Lyman, what is it? The Lyman, the answer is UV. For Balmer, the answer is visible. For Pascal, it's IR, bracket, Fund and everything is IR. So this can be an MCQ. In your exam, they can give you any one. They can ask, in which region of the electromagnetic spectrum does Lyman series lie? You should say UV region. Okay? Alright, is that clear? Okay. Next is the de Broglie explanation of Bohr's quantization rule. Now, what did de Broglie say? So de Broglie said that the wavelength is related to orbit in the form n 2 pi r is equal to n lambda. Okay, so that is how they are related. Now, de Broglie has also given us an equation, lambda is equal to h by mv. Now, we will substitute that here. So, 2 pi r is equal to n into, instead of lambda, I'll write h by mv. Okay. Now what I will do, I will just cross multiply. MVR is NH by 2 pi. I just cross multiplied this. MVR is NH by 2 pi. Now what is NH by 2 pi? It is the angular momentum. So L is equal to MVR by NH by 2 pi. So this proves that angular momentum can only take discrete values. See, angular momentum cannot be L is equal to 0.5 h by 2 pi. It can only be 1 into h by 2 pi or 2 into h by 2 pi or 3 into h by 2 pi. It can only take discrete values. It cannot be any random value. Alright. Is this clear? Yes? Can I have some fire in the chat if this is clear to you? Yes, students. Yes. Next is nucleus. For nucleus, it's very easy. What is it? You know what is binding energy? So binding energy is something that indicates the stability of the atom. So if an atom has a very high binding energy, what does it mean? It has a greater stability. That means the electrons are very closely attached to it. Now what are isotopes? Isotopes have same atomic number but different mass number. Isobars have same mass number but different atomic number. Isotones have same number of neutrons but different atomic and mass number. I've given you some examples as well here. These are very easy portions. You can definitely learn these. Right? Very easy. Right? Okay. So the size of the nucleus is proportional to A raised to 1 by 3. Alright. The size of a nucleus is proportional to A raised to 1 by 3. Now what is R equal to? R naught A raised to 1 by 3. This R naught is a constant. It is typically 1.2 femtometers. A is the mass number. So this is the size of the nucleus. Alright. So size of the nucleus is always proportional to the mass number. So higher mass number, higher size of the nucleus. Alright. Why is the size of the nucleus proportional to mass number? Because mass number is the number of neutrons and protons. Okay. Yes. 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 Is this clear? Yes, this side. Okay. Next is properties of nuclear force. What are the properties of nuclear force? The first thing, they're attractive, they're short-ranged, they're charge independent, they're spin dependent, they're exchange force. Nuclear forces are saturated force. So for example, you will write nuclear forces are strong attractive force, nuclear forces are short-range forces, nuclear forces are charge independent forces, nuclear forces are spin independent, nuclear forces are exchange forces, and nuclear forces are saturated forces. Okay. Now, what are these? Attractive means just attractive. Protons and neutrons, they're attractive. And then short range, which means these particles are very close together. So, they are short range forces. And they're charge independent. Alright, they don't depend on the charge. They don't depend on the spin. They also are mediated by exchange particles. Okay? Now, saturated forces. They do not interact with a lot of neighbors. They interact with a very little limited number of neighbors. Alright? Okay. Next is nuclear fission and nuclear fusion. So what happens in both of these, I want you to know. So in nuclear fission, there is a heavy nucleus. This heavy nucleus is unstable by itself. So this heavy nucleus splits into two lighter nucleuses. Okay? So heavy nucleus splits into two lighter nucleuses, that is nuclear fission. It can take place at any temperature, and every time a heavy nucleus breaks into two light ones, energy is released. Alright? And then, it produces radioactive waste as well. But what is fission? Fission is when you have two light nucleuses like hydrogens. You have two light nucleuses, they are unstable. So they combine together to form a heavy nucleus. So this requires very high temperature, and there is energy that is released per fusion is very low. This does not produce any radioactive waste. Why? Because the end product is completely stable. Okay? Why they are not dependent, as in dependent on what they are? Yes? Okay? Is this fine? So fission, one heavy element splits into two light. Fusion, one big element splits into fusion, two small elements fuses. Fusion is fusing. So two small elements fuse to form a heavy nucleus. Okay? Okay. Next is semiconductors. What are semiconductors? Semiconductors are definitely between conductors and semiconductors are between conductors and insulators. Okay. So, what are the properties? First thing, you have to look at the diagram. So, you can see the conduction band and the valence band are merged for a conductor. There is no gap. That is why it is able to conduct very well, because the electrons from the valence band can easily move to the conduction band. But if you go to a semiconductor, it has a small energy band gap. Only if this band gap is overcome, it can conduct. But in an insulator, the band gap is very big. That is why they don't conduct. So an example of an insulator is plastic. Plastic do not conduct electricity. Why doesn't plastic conduct? Because from the valence band to the conduction band, the movement of electrons is impossible because of the huge band gap. In semiconductors, there is a band gap, but it is overcomable. You can transfer. In in conductors, no band gap at all. Okay. So what about its resistivity? For semiconductors, it's very low. For semiconductors, it's moderate. For insulators, it's very high. Okay. Now what about current flow? It allows current to pass through. It may or may not. Insulators, never. Okay. Now conductivity decreases with temperature, increases. Conductivity is zero because it's an insulator. Conductivity is due to free electrons. In semiconductors, it is because of electrons and holes. In insulators, no conductivity. Okay. Alright. Now for the spin, Archana, see here, it does not depend on spin, as in each atom has a spin. Each particle has a spin. Okay. So that at this level, you will not be able to understand. That when you go to do physics in higher levels, you'll be able to understand. Right now, you just have to know that it is spin dependent. Okay, it depends on spin. It is not independent, it depends on spin. It's a little more higher level of physics. Okay. Alright, now we looked at all three: conductors, semiconductors and insulators. Now, in semiconductors, we have two types: intrinsic semiconductors and extrinsic semiconductors. An intrinsic semiconductor is a pure semiconductor. Extrinsic is a doped semiconductor. Okay. So, in a pure semiconductor, conductivity is because of holes and electrons. But in extrinsic, it is mainly due to the majority. So, whatever you're doping it with, doping is like mixing. Okay. This is a pure semiconductor, you're mixing it with another impurity such that you increase its conductivity. Now, if the impurity has more electrons, then the conductivity will be because of electrons. If the impurity has more holes, then the conductivity will be because of holes. Okay. So purely semiconductors have no conductivity. You can see there is a band gap. Now, how can you reduce the band gap? By adding impurities. That is why doped semiconductors have high conductivity. Alright. Now, in pure semiconductors, number of holes and number of electrons are the same. But in doped semiconductors, it varies. Why? Because it depends on the doping that you're adding, the impurity that you're adding. And again, it depends on temperature. Okay. Next is the properties, the difference between P-type semiconductor and N-type semiconductor. So, P-type semiconductor has trivalent dopants. N-type has pentavalent dopants. What does that mean? Trivalent dopants means 3. Penta means 5. So, P-type will have 3 electrons coming. Okay. So, imagine to a silicon, I had 3 more electrons. Silicon actually needs 4 more. So, there is an extra hole there. So, it becomes a P-type, positive semiconductor, because it has an extra hole. Now, what is pentavalent? Let's say I have silicon which has 4. I bring 5 more electrons, but silicon only needs 4 more. So, this extra electron is what contributes to the charge. So, that is why it is an N-type. Extra is electron. So, P-type extra will be hole. Okay. So, the majority charge carrier will be hole in P-type, and for N-type it will be electrons. Okay. Yes. Next is forward biasing of a diode. So what is forward biasing of a diode? When the P-type is connected to the positive terminal of the battery and N-type is connected to the negative terminal, then that is called as forward biased diode. Okay. Now during the forward bias, you actually want to conduct properly. So the depletion region, what is depletion region? Depletion region is the region between a P-type and an N-type. So the region in the center where holes and electrons recombine, in the center it's called as the depletion region. So the width of the depletion region has to decrease for forward bias. It's like a door. So the door has to open. Only then the conductors can pass through. So for forward bias, the door is open. Width of the depletion region is less. Junction potential is less. Small resistance and current is due to majority charge carriers. And you will get a graph like this. Current is flowing. Okay. Now for reverse bias, what happens? You can see the P-type is connected to the negative and N-type is connected to the positive. So in this case, it is not a proper way of connecting. It is a different way. It is not forward biased. So the width of the depletion region is very high, which means it's like the door is locked. The door is locked and 2 people are standing in front of it also. So that is reverse biased. Okay. So what happens? Width of the depletion region increases, junction potential increases, very high resistance, and minority charge carriers are the ones that are actually conducting, not the majority. So in p-type, what is the majority charge carrier? P stands for holes. But if it is reverse bias, electrons will conduct there, because conduction is mainly because of reverse biased and minority charge carriers. Okay. Next is the rectifiers, half wave rectifier and full wave rectifier. So what happens in a half wave rectifier? You have only one diode. So if you have an AC signal, only one half cycle is being transferred. Only these positive half cycles are transferred through the diode. During the negative half cycle, there is no diode. See, what is the specialty of a diode? The diode only conducts current in one direction. So a diode cannot conduct current in both the directions. So you can see there is only one diode. So it conducts current in every positive half cycle. So you can see the output is positive. Alright. But in full wave rectifier, what happens? You have two diodes. Okay. And the two diodes are connected in two ways. So if this is a signal coming, when this positive half cycle comes, D1 will conduct. When this negative comes, D2 will conduct. So D1 can only conduct in positive, D2 can only conduct in negative. So what is your output? You will always have an output. Why do you always have an output? Because you have two diodes. And both the diodes are forward biased in one case. D1 is forward biased during the positive, D2 is forward biased during the negative. Okay? Is this clear? Yes. This is half wave rectifier and full wave rectifier. Are you all there with me? Can I have some energy chat in the chat, students? Some fire. Now I have some MCQs. We'll quickly do some MCQs and wind up today's class. Is that clear? Is that fine? Yes, Paka questions. Yes, Archana. These are all very important topics. Okay? If questions come from this, you will be lucky. These are all previously asked important questions. This is a passing package. Not for you to score center, but the passing package. Okay? Yes? Are you interested to do some MCQs? If you want to do MCQs, we will solve some MCQs now. Quickly, can you let me know in the chat? So many people requested for MCQs. That's why I have some MCQs. Oh yes, Monkey D. Luffy is back. I missed you. Swati, Kartik, Sahana. Yes, shall we do some MCQs? Okay. Yes, no. Paka ma'am. Yes. Okay. So I want you all to tell me the answers for the MCQs. First question. These are not going to be as difficult as your KCET MCQs because these are your PU MCQs. Okay. First question. What is the SI unit of electric field? Quickly tell me the answer. A, B, C or D? A, B, C or D? What is the unit of electric field? Electric field. Electric field. D. Okay. The answer is option C, Newton Coulomb. What is electric field? Electricity has the unit ampere, but electric field has the unit C. Anybody said C? Yes, Kritik, very good. It is C. Yes, Kritik, very good, very good. It is C. Very good. Superb. Yes, Pradeep, it's C. Yes, Archana, it's C. Yes, yes, very good. Now, what about the next question? Quickly tell me the next question, all of you. The potential energy of a system of two charges is positive when the charges are unlike, at infinity, 0. Quickly, can I know some answers? Yes, students, can you quickly tell me the answers? Are you all there? What is the answer? Like charges, unlike charges. So many are saying C, B, A. What is the answer? Pakka D. But I would say it's Pakka A. It's like charges. Yes, very good, Ravinder. Yes, Kritik. Okay. Next one. The resistance of a conductor is directly proportional to. What is the formula for resistance? Resistance of a conductor is directly proportional to. See, resistance is rho L by A. Resistance is rho L by A. So it's directly proportional to what all? It is directly proportional to A. Okay, I have so many A's. But what about temperature? Isn't it proportional to temperature also? When temperature increases, resistance will increase. So the answer is going to be both A and C, because when temperature increases, resistance will also increase. Next question. The force on a charged particle moving in a magnetic field is maximum when angle between the velocity and magnetic field is. What is the answer? Can I know the answer? Yes. The magnetic force on a moving charge is given by what? F is equal to QVB sine theta. So the force is maximum when theta is 90 degree. Very good. The magnetic susceptibility of a paramagnetic material is. What is it? Magnetic susceptibility of a paramagnetic material. What's the answer? What is the answer? Yes, very good. It is positive and less than 1. This I've already taught you in last class. In an AC circuit, the power factor is. In an AC circuit, the power factor is. Yes, superb, superb. It should be between 0 and 1. Next one. The speed of electromagnetic waves in vacuum is. Very easy. It should be equal to the speed of light, which is 3 into 10 raised to 8 meters per second. Any electromagnetic wave should have the speed of light. Next one. The focal length of a concave lens is. What is the answer? Focal length of a concave lens. So a concave lens is like this. So focal length is going to be where? In front of it. If it's in front of it, it's always negative. Okay? Yes? Yeah. Now, in Young's double slit experiment, the fringe width is. The fringe width is. Yes, can I know the answers? In Young's double slit, the fringe width is. B. I have so many B's. Anybody saying, yes, Archana, very good, it's A. Yes. Yes, Kritik, it's A. Kritik has got almost all the questions right. It is directly proportional to the wavelength. Yes, Singer Pecky, it's A. Yes, good, Ravinder, good, Luffy, good, Sahana, very good, it's A. Next question. Question 11. Dual nature of matter. It's from dual nature. The de Broglie wavelength of the particle is given by. This also we discussed today itself, so you should tell me the answer. Yes, obviously. Lambda is h by p. Energy of an electron in the nth orbit of hydrogen is given by. What is the answer? Yes. Very good. It is what? Minus 13.6 by n square eV. Which option is that? Option A. Very good. Superb. The mass defect of a nucleus is. What is mass defect of a nucleus? Read all the options. Is it the difference between the mass of the nucleus and the sum of mass of its constituent nucleons? Or the sum of the masses of the nucleus and its constituent nucleons? Mass of the nucleus? Obviously, option A. What is mass defect? The difference in the mass between the nucleus and the nucleons. Okay? Superb. Very good, all of you. Next, semiconductor. In a PN junction diode, the region where no charge carriers are present is called. Yes. Super. Very easy. Depletion region. Now, the process of converting an analog signal into a digital signal is called. What is this process called? So this is a little out of question, but yeah, you can answer it. What is it called? What is it called? A. Modulation. Is it A? 11th question, what happened? Is it A? I didn't say it's A. When I just said A, everybody is putting A. It's actually sampling. It's a bit out of question, but still. Okay? The focal length of a convex lens is, if concave was negative, convex definitely positive. Now, the angle of diffraction in a diffraction grating is always directly proportional to wavelength. Okay? Yes? Now, question 18. Electromagnetic waves are what kind of waves? Longitudinal waves or transverse waves or both? See, nothing can be both. Okay, so, things can be both but not electromagnetic waves. 15th question. 15th question is from communication system, but you don't have to learn that. Okay? You can ignore that question. Okay? What is the answer to 18? 18. C. No, not C. B. Yes, good. Amulya, very good. It is B. Yes, it is transverse waves. Yes, Kritik, it is B. Now, question number 19. Alternating current. In an AC circuit, the impedance is opposition to current flow, maximum current, average current, maximum voltage. What is impedance? B? No. It's not B. See, impedance is just like resistance. It is the opposition to current flow. Okay? Now, I think this is the last question. Yes, last question. Quickly, last question. Electromagnetic induction. The induced EMF in a coil is. Yeah, induced EMF in a coil is. This is a question based on the very famous Faraday's law. What is Faraday's law? If you know Faraday's law, you will get the answer to this. What is it? What is it? Nobody is answering. Did you already answer? Yes, Ravinder, it's A. Very good. Faraday's law, directly proportional to the rate of change of magnetic flux. Okay? So these are some MCQs. Very few MCQs I have done. Yes, Pradeep, it's A. Very good. Faraday's law. Yes, good, Sahana. Good. It is A. Very good. Okay? Yes? Yes, Amulya, very good. Okay? So right now we have discussed all of second PUC important topics. All this is more than enough for you to pass. This is a passing package, not a package to score centum, but a passing package. Okay? I have just discussed some MCQs because so many people, requested for MCQs. Oh, my Sahana's here. Sahana's, always keeping count of my likes in my videos. And today she says it's 83. Quickly, students, please go like it, make it 100. No problem, Archana. Okay? Quickly make it 100 likes and let's end the session. Okay? Is it clear? I wish all of you the very best for exam 2. Okay? Don't worry. You can definitely kill it. I have trusted each one of you. You will all do very well. Okay? This is just like a revision for you to know what all is there because it's been some time since you studied it in school, no? Okay? So I'll see you all. Are you all happy? Yes? Scoring package. Scoring package, you know how to score, no? Because you're all very smart students. Alright, let's wind up. So bye-bye. I'll see you all with another video. We will definitely be starting NEET soon. Okay? If you're all waiting for the NEET classes, can you all put some fire in the chat so we know that you all are interested in NEET and we can do it. Okay? Meanwhile, go like the video, share it with your friends, subscribe to our channel. Okay? So I'll see you all with another video. Bye bye.